engineering, Floquet engineering. And yesterday, and we are continuing today, we're talking about graphene first. So we started with a spin half. So your homework yesterday was to solve the same problem for a spin 1. And then we moved on. Now we are talking about solid-state systems. And our first case is graphene. It's going to be basically our only case, the only case we are going to address. All the other ones follow naturally if you consider graphene. We have everything that we need. So it's a honeycomb lattice. It's a honeycomb lattice. And then we defined the tight binding model without time dependence yesterday. And today we are going to consider the case with time dependence. So that is what is going to be novel in this lecture. Yesterday we also commented that we can find what is the time dependence by a Paros substitution. So the Paros substitution is a way to connect electromagnetic fields with matter. So the Paros substitution in graphene, the Hamiltonian, that is now going to be an explicit function of time, is minus th sum over I and j. Ci dagger Cj, this is what we had before, but now we are coupling it with radiation, so we have this exponential of minus I line integral from Ri to Rj a dl. This is the novel term. And as I told you yesterday, you can choose the vector potential the way you want. So the vector potential is typically a function of time, and this is part of the protocol. So the choice of the vector potential is part of the protocol. And yesterday I told you that one very specific choice that is quite interesting is circularly polarized light. In that particular case, A of t becomes A0 cosine of omega t sine of omega t. This, as we're going to see, this term is going to open up a gap in our spectrum. And what we have here is the time-dependent problem that we need to solve. So again, we defined these delta terms that are the nearest neighbor hoppings. So we had 3 of them last lecture. And we concluded that the Hamiltonian for graphene is something like this. A, B dagger 0 f of k star 0 a of k, b of k, summed over k. This is the Hamiltonian in equilibrium for graphene. So in today's lecture, we want to solve the problem with the time periodic potential. So that's what we're going to be doing today. I will not be doing all the calculations because they are pretty straightforward. But what is going to become clear is that if you want to find the HM, so HM are the Floquet terms, what you have to do, you're going to have to integrate over time here. So you're going to integrate over time, and this is the first time that we're going to see some particular functions that appear a lot in Floquet engineering, and I will give some expressions for them. And these are the Bessel functions. So recall that we have this class of functions called the Bessel functions. So the Bessel functions. And I'm going to list here some representations, integral representations of Bessel functions. And you can keep this in your notes. And every time that you need those relations, you can just go back and look them up. You can find them and use them as many times as you want. So I will give you 3 integral representations of Bessel functions. This is the first one. So we're going to be using Bessel functions of order, they are of first kind and of order m, let's say. So I'm going to represent as Jm of x. This is a Bessel function of order m, and the argument is x. So let me just list some properties of them here. In particular, they are integral representations. So it's 1 by 2 pi, integral 0 to 2 pi, d theta, e to the I theta times m, e to the minus ix cosine of theta plus alpha. So this is one of them. Oh, sorry, here I'm missing exponential of minus im alpha. So this side has also this. Another one that appears a lot is Jm of x. e to the minus I alpha m. This is 1 by 2 pi, 0 to 2 pi d theta, e to the I theta m e to the minus ix sine of theta plus alpha. If you read most of the papers in Floquet engineering are going to have a vast collection of Bessel functions. And the reason for that is this integral that we have to calculate. This integral becomes immediately an integral like this. You can already see that. You can already see that because recall that to find our HM, you have to do an integral, right? HM was 1 by t, 0 to t dt, e to the I m omega t, h, and recall that this h is actually a function of omega t. This h was a function, it's a time periodic dependence. And this can be rewritten as 1 by 2 pi, 0 to 2 pi, d theta, e to the I m theta, h of theta. This is an operator. All of them are operators, okay? So quite often you're going to have to evaluate something like this. Okay, but this is the general problem. But our h of theta is very specific. So we have this phase. We're going to have a phase that if we just compute this integral from Ri to Rj, notice this vector potential is time dependent, but it's not position dependent. So what do I mean by that? We had our graphene yesterday. So graphene, a layer of graphene. We had our honeycombs. And then our proposal, the protocol, was to shine light perpendicular to the sample. So this is the direction in which light propagates. So this is the light propagation. And some questions that I got after the lecture yesterday, let me just address them now as well. So if light propagates along this direction, there is this k of light. This is the momentum carried by light. It's typically very tiny. And both the electric and magnetic field are along this plane. So E and B are perpendicular, and along this plane, they rotate, and always perpendicular to the momentum carried by light. Okay, so A is perpendicular to B, and both A and B are perpendicular to this K. So if I stay on the surface of this particular plane, the vector potential does not have any explicit position dependence. I say that this plane is, for example, at z equals to 0. This is the position of the plane, and that's it. So the only thing that I actually have is a time dependence. A time dependence is already enough trouble, so we don't need also a position dependence. So if we only have this time dependence, and again, everything here is easier if you write as function of omega t, because that's what it is. You can compute this integral. So let's call this 1. So 1 is equal to what? It's this integral here. It's going to be e to the minus I. So this integral can be done is Rj minus Ri dot A of t. A of omega t. Okay? So that's quite an interesting result already. Okay, you can compute this dot product and so on. But it tells us that the different directions along the lattice, so recall that this Rj minus Ri are different points along the lattice. So it could be a point here and a point here, for instance, okay? Or a point here and a point here. They will acquire different contributions from this time oscillating phase. In other words, end of the day, our vector that connects the nearest neighbor sites will appear explicitly here. So we can even call this delta ji. Delta ji. Okay? In principle, this could be the phase acquired by any 2 points of your lattice. But as we know, this is only nearest neighbors. So these 2 R's are going to connect nearest neighbors. So I suggest you go back to yesterday's notes and recall what are these delta L's. Delta L is cosine of phi L and sine of phi L. And then you can take this dot product with A of omega t, you're going to get a cosine and a sine. You do a little bit of trigonometry, elementary trigonometry, and you can cast your oscillating term like this. The question is to find alpha. Doing a bit of trigonometry, determine what is alpha. And when you do this, you can compute this integral, and this is what you get. Okay? I'm not going to do all the steps in this calculation. It will take 10 to 20 minutes, but this is the general way of doing it. You draw. My suggestion is to do it as geometrically as possible. So you draw these honeycomb lattice, and you call this the x and y plane, and then you have light that is going to be rotating along this plane with some angle theta. And then you have another angle here by this bond, and then you see all the angular differences. And you can recast in this particular way. If you have questions about this, you can ask me later. This step is always done when you're doing this type of calculations, okay? I will not do them step by step. The only thing to recall before we move on is the shape of Bessel functions. So some properties of Bessel functions that are important. So, as you may recall, for small x, Jm of x goes as x to the power m if m is not 0. Okay? And finally, J m of minus x is minus 1 to the power m Jm of x. These are all the ingredients that you need to know to do this calculation, okay? And now I will go to the results that we get by doing that. So we can discuss a little bit about the physics. So the result of this calculation that I just proposed is the following. So we can find that there will be a hopping between different Floquet sectors now, obviously, because we are going to find HM, and HM will mean that you hop not only from one point to the other point of the lattice, but as you hop from one point of the lattice to the next point of the lattice, you also absorb or emit M photons. So you change the Floquet sector by going from this point to this point. So that's why we acquire an index M here. So you're changing the position on the lattice, and you're also changing the number of photons. And this is going to be TH. This is the equilibrium value. So yesterday I called this equilibrium value. Okay. Times e to the im phi ij. So this guy now acquires also a position-dependent phase. It depends on which 2 points you're hopping to, times the Bessel function m of A0. And I will do just a little bit of, I'll change, it's already here. So the notation is A0 is the amplitude here. So this is what enters the calculation. Expressions like this, you're going to find everywhere. So this is, I'm putting this expression here for you once. You're going to find in basically all papers in Floquet engineering of solid state physics, Bessel functions that are going to mediate this photon exchange. Phases, because it does depend on where you hop along your lattice. And the original stationary or bare value of your hopping. So just to be precise, phi ij in general can be written minus arc10 of rix minus riy divided by rjx riy minus rjy. So it's the difference in x coordinate divided by the position, the difference in y coordinates. And again, I will leave you, this is I'm trying to be as general as possible. You can apply this to the square lattice. This was one of the homeworks yesterday. I think it's the last homework, last question. You can just apply this. You can do this for the square lattice, for the triangular lattice, and so on. For the honeycomb specifically, obviously these differences are not arbitrary numbers, as we recall. You can just see here what are the possible differences. You do trigonometry, right? So you have the angle here, so you know what is the difference between this x position and so on. You just plug them here. You're going to get only 3 possible, a small collection of possible values for this phase. And I suggest you to collect all of them. So I will leave you as an exercise because we don't have time. What are the possible phi ij's for graphene? It is like this. It is like this. And there's a minus sign as well. You have to really do this trigonometry properly. And then when you do this, you'll get this phase as well. So oh, sorry. This is a different phi. This one has nothing to do in principle with this guy here. Okay? So here L is 1, 2, and 3. And to avoid this, let me just say that, for example, this is cosine of some number, some pi by 3, and sine of pi by 3. But that's, thank you, that's a good point. This phi is just, we are running out of Greek letters. But this is just, by definition, this guy. By definition, this guy. Okay? Any other questions? So we have everything that we need. These are the hopping terms, but the problem is not yet solved. The problem is not yet solved. We're just learning that if I hop, I can hop from here to here. And now with this TH, that also carries this label M, which means that from here to here, I'm in different Floquet sectors. That's what we are learning so far. Now we have to actually solve this problem, okay? To solve this problem, you need perturbation theory, our perturbation theory that we did yesterday. To be honest, this is not completely true that we need the perturbation theory. There are several limits in which we can solve exactly. In particular, you can exactly see what is the gap that is going to produce. It's a non-perturbative result. So at the gamma, or at positions, we had cones, as you may recall. I will show some band structures today. But as you may recall, we had cones. And now we have the light. Let's represent light schematically like this, light. It's going to gap out. It's going to gap out. I'm already giving you some spoiler. It's going to gap out. And then there's a gap here that we can call delta. This delta can be computed exactly. I will tell you a bit later today how to do it. It's a simple problem. It's here, as you may recall from the spin half problem, this is a 2-level system here, basically. So you can solve the 2-level system. That's completely fine. So you solve it here. You get the exact value of the delta. It's completely similar to what you did for what we did together for the spin half. Completely similar. Okay, so, but for general brain structure, can I erase this or do I leave it here? Oh, let me leave it here. I don't know if everybody's, because we have some people missing now, so I don't know. Okay, so, all right. So let's do our perturbation theory as we discussed yesterday. As we discussed yesterday, if you want to find an effective Hamiltonian, an effective 2x2 Hamiltonian, because we had, why 2x2? Because graphene has 2 bands. Okay, this 2x2 comes from the 2 bands. So we had our good old H0, and I will emphasize once again that H0 is not the equilibrium Hamiltonian. H0 is the time average of the time-dependent Hamiltonian, plus sum over m not equal 0, 2m omega, and h minus m hm. If there is a sign that I'm getting wrong, please let me know. Okay, so as I told you, H0, and this I will write down what this Hamiltonian is. So what is the task? So if you know the hoppings, you know HM. The HM is the hopping times the second quantized operators. And then you can just commute them the same way as we did yesterday. Yesterday, I wrote down 3 or 4 very useful relations to commute fermionic operators. You want to write down commutator of fermionic operators in terms of anti-commutators. You just apply that with these effective hoppings. So just to write it down, our HM is going to be our THM, sum over nearest neighbors, CI dagger CJ. Okay, you just take this, let's put a hat, you take this to our commutator, and then you just commute them, very nice, and you discover what is new. So I will write down this, what is H0. So H0 is going to be minus TH Bessel function 0 of A0, sum over I and j, Ci dagger Cj. So it does acquire a Bessel function, because if you average this function here, that we have, the time-dependent function, over a period, you're going to get for free a Bessel function. A Bessel function that we don't always want, actually. Sometimes this Bessel function doesn't help us. Sometimes it does. A property of Bessel functions that I would like to point out at this particular moment is that J0 of A0 looks something like this. Okay? So it starts at 1. It can change sign. That can be extremely exciting if you're doing, if this is true for, let's say, a ferromagnetic problem, you can change it to ferro to antiferro and so on. But we're going to see that for magnets, life is more complicated than this. But you can also suppress the hopping. This is also interesting. It can lead to localization in some systems, okay? You choose this is A0, this is the fluence, this is the intensity of light. You can fine-tune to a 0 of this Bessel function, you know the zeros, and at that particular point, the hopping vanishes, okay? This. Right, right. This is about the protocol. So the protocol is the following. Recall our protocol. We could choose the frequency, and here I'm assuming the frequency is much larger than TH. So I'm not playing with frequency here. The frequency will be just a denominator. It won't do much. Let's assume that the frequency is much larger than TH. But A0 is intensity, basically. It's actually square root of intensity. I have to bring all the units back. So what you know, like if you go to a lab, you know the intensity of light. Intensity of light is the square of the amplitude of the electric field. And the amplitude of the electric field is related to the vector potential by minus dt of A. So you get a factor of omega as well. But it is true that you can change this intensity. This is something that can be changed. So if you change the intensity, you change A0. So in principle, experimentally, you can walk around here by changing the intensity of light. So let me emphasize again. I already chose circularly polarized light. So this is only true for circularly polarized light. This can easily be changed. Choose other polarizations. Then the result is different. This is the result for circularly polarized light. And then you can change this fluence or intensity to walk around here. So these are the effects only on H0. And again, I'm doing this for graphene, but this is true. This equation is basically true for any tight binding problem. There's nothing here is specific for graphene, okay? The next term involves this commutator. And for this one, I will be a little bit more specific and just write down what is the answer for graphene. Okay, so as an exercise, you can commute HM and H minus M, as we described yesterday. And you can already see by the structure of this commutator that if I and J are nearest neighbors, now you can hop here and back here. So this is going to be TH of minus M, and then you arrive. This is what we get from commuting the I and J and the structure, M minus M from the commutator. So in principle, graphene, in equilibrium, these two sides were connected, but these two sides were not connected. Now these two sides are connected. So that's already something new. We didn't have this before, okay? We didn't have a connection between these two sides. You can say, well, okay, but you have this 1 by omega denominator. So this is probably very small. Possibly. But does it lead to new physics? In other words, if this term just changes the cone a little bit, just, I don't know, tilts this line, does something like this, not particularly interesting. It will be a subleading term. But it does this, okay? That's what is novel. It gaps out the cone in a very specific way. So let me write down what is the expression for this coupling. So the new coupling is going to be the following. So let me call even this delta H. And I'm completely aware that I'm writing many H's, okay? So this is going to be our delta H. And it's going to be sum over I and j, such that I and j are next nearest neighbors. This follows trivially from the structure of the commutator. I, some k effective. This part is not obvious. It's a very interesting exercise to find this. You are correct. I'm sorry. You are completely... In principle, you are correct. Let me just put this inside this sum. Yes, you are right. Sum over I and j, th, m, which in principle is a function of I and j. It's a very specific function. In fact, there are only 3 or 4 different values, but in principle, correct. There is a dependence here. I and j are next nearest neighbors. Tau ij, ci dagger cj, where I times k effective is minus 2I by omega, th squared, sum over n from 1 to infinity, jn squared of a0, divided by n. This looks harder than it actually is to compute. If you do a little bit of geometry, you're going to be already convinced that it has to be like this. Times sine of 2 pi n by 3. Okay. This number is interesting, but it's a number. If for a given a0, you sum this. But what is even more interesting is the tau structure that we're going to address now. Question? Second order, yes. Yes, you hop once, you hop twice. This is interesting, sure. There is a function here, you sum over n, very nice. But the most interesting feature is the tau structure. So tau works in the following. Tau ij is +1 clockwise and -1 counterclockwise. Okay? So yes, there is a site dependence, but a very specific one. So looking to, let me draw the lattice again, just to emphasize what this term is doing. Okay, drawing the lattice again. What is happening is, if I can connect this side to this side. So the electron will try to come from here to here, and then it will jump from here to here, and then it will jump from here to here. This process in which I destroy an electron here and create an electron here is surely, if I call this J and if I call this I, it's a process of the form Ci Cj dagger. It will have some I in front. It will be Hermitian for sure, because if you do it the other way around, you get the opposite sign. But then you need to know what is the number in front. So I'm telling you, this is a clockwise operation. The electron is trying to move like this, just like the clock. So it's a plus. So it's I, K effective. This is the hopping. So from here to here, you get this I, and I. If you do it the other way around, it's minus I. And then you can ask, well, this is a bit strange. Why do electrons prefer to hop one particular way with a phase, the other way with the opposite phase? The reason is from the light. So recall that we are considering circularly polarized light. So circularly polarized light rotates in one very specific way as well. And you can see if it's like this or the other way around. So this is circularly polarized light. If you reverse this polarization, So circularly polarized light has two flavors, left and right circular. There are two ways of having this light, left and right circular polarized. One is like this, and the other is like this. And if you change one from to the other, you get the other model, the other way around. It's not very different. The effects are the same. In terms of Chern numbers, you're reversing the sign of possible Chern numbers, but it's going to gap out. At this point, you okay? Yeah, we could cancel this I here. That's okay. Yeah, IKF is already this, because otherwise you'll have to, yeah, this and, okay. You still have an I left. This is very important. Okay, very good. You can tell me, I already know what this model is. I know how to solve it. It's the Haldane model. Yeah, you're exactly correct. This is the Haldane model. It's called the Haldane model. And if you're familiar with the Haldane model, you can use all the technology that you know about that particular model. In particular, there is a gap. And this gap is going to be proportional or only happen when you have this particular term, not the other one. This term is still gapless. It's a graphene. This is still graphene with a different, around the Dirac cones, this is going to give a different velocity. It's going to renormalize or renormalize down the velocity because it's decreasing the hopping. But this is the Haldane model on the honeycomb lattice. There are so many Haldane models. We need to specify which one it is. And now I will use some information that is known. Otherwise, I would have to diagonalize it. It's gapped. It's chiral. Chiral means that the electrons hop clockwise and counterclockwise differently, not the same way. So this has some chiral effect. And it's topological. Topological. You can compute Chern numbers and everything the same way as Haldane did. There was a very interesting question yesterday about spin indices. You can tell me, well, but these are electrons. Why don't I write C I sigma? What am I doing with spins? I'm just assuming that spin up and spin down behave the same way. You can say, well, this is not a very good assumption if you're shining light because you have a magnetic field now. So you could, in principle, have a Zeeman term. The answer is yes. But if you compute how small this magnetic field is going to be, you can see that you can neglect this B dot sigma term completely. It's very, very small. This is true for light in general. It's not easy to produce large magnetic fields. So what the light is doing effectively is completely related to the orbitals. It's the orbital degrees of freedom are giving you some chirality. So if you were to put the sigmas here, you would write something like this and create two copies, okay? This is not, but let's consider spinless fermions. That's not a big issue here. Okay, this I think is basically what I had to say about graphene. You can choose other polarizations. If you don't believe me that this is coming from circularly polarized light, you can just consider linearly polarized light. I must already tell you that circularly polarized is the easiest to compute. The other ones are not so hard, but what is different about linear polarization as compared to circular polarization? So circular polarization rotates like this. So it draws a circle. So this circle brings some chirality to the problem, but doesn't necessarily break many lattice symmetries. What do I mean by many? It breaks mirrors. Mirrors know about chirality. But it does not break the equivalence of some of the bonds. So let me draw the honeycomb again to tell you about linear polarization. So again, we are exploring knobs now. So the frequency, I think we already understand. It's large, it's here, much larger than TH. A0, we understand. We can change, these functions are going to change like this. And just to tell you, the other Bessel functions, they start from 0 and they go up, and then down again. And they go up painfully slowly, as A0 to the power n. Okay? But now, what about these two knobs we understand? So what about polarization? And polarization I consider to be one of, if not the most interesting one of the most interesting knobs in Floquet engineering. So if you consider linear polarization, this is also one exercise that I included in your homework set. So let's say I put linear polarization along this direction here. So the electric field now oscillates like this, unlike the circularly polarized one that oscillates like this, goes like this. So it just oscillates like this. Clearly, there is no reason to expect this bond to behave the same way as this bond. They are going to be renormalized differently. Okay? They're going to be so if you have a system that is initially isotropic, you're going to break that. Typically, this is not so good. But if you're very optimistic, I will give you an example. If you have, let's say, the simplest that I can imagine is a triangle. So if you have a triangle, and then let's say that you have here T hopping 1, and here T hopping 2, and here T hopping 2, and you're not particularly happy with this anisotropy, well, my suggestion would be consider some linear polarization along this direction here. Along this direction, okay? It's going to change, or in any, or along the diagonal, any linear polarization. You can choose a posteriori, which one helps you the most. But to zero further, the ones that are parallel to here will acquire an immediate Bessel function. So this guy, I will not do the calculation, but it will acquire a prefactor that is a Bessel function. As I told you many times, the price to pay is that this is going to renormalize down your hopping. If you want to study localization, that's great. If you want to study magnetic properties, not so great, because having a not so small t is important, as we're going to talk about tomorrow. Okay, do you have questions? No. And then you compute the integral, yes. That's all you have to do. But this, it's not obvious that you're saying inside the argument of the Bessel function, because this A0 is not going to be A0 anymore when you do the integral. Yeah, right. I can show you later. Maybe I have even one of my, let me see if I have here in the next slide. It's raining now, very good. Okay, this is just because Neto asked, so I already had a slide prepared for his question. I already had this pre-prepared for his question, so let me show this slide. Polarization is a tuning tool. Since we're discussing something along this direction, we have some drawings here. Polarized light generically breaks asymmetry, so this is our good old circularly polarized light. It rotates. Linear polarization is like I drew here. But if you have the T1s and the T1 prime, you can do what Neto proposed, field along this direction, you get these cosines here. So you're going to renormalize down T1 with this Bessel function, and now the three of them are equal, okay? So you can, it is an important tool to fix if you have anisotropies. It may not be the easiest thing to do to fix anisotropies, but it's a possible thing to do, okay? All right. This is the basic solution of graphene. I can tell you some, I will show you just one slide to tell you about the measurements that were done for this material. Again, when we start with graphene. Yesterday I was also asked, why not to show the band structure of graphene? It looks so nice. Okay, this is the full band structure of graphene without light. The two direct cones are, you can naively infer that there are many cones, but some of these points are equivalent. They are not different points. They are connected by a reciprocal lattice vector. So you have two inequivalent cones, and then we shine light. And this is what I just described on the board. You absorb the photons, you emit the photons. And this is the proposal. It's going to gap out as I proposed here. You can calculate this. I will even give an argument of how to compute this gap now. And you have chiral edge states. And this is a consequence of the Haldane model. Haldane solved this problem. This week, we're not going to be resolving problems. We're going to, that's why we call it engineering. We're going to engineer the model. And if we have the solution, we use the solution. If we don't have the solution, we find the solution. Yes, these are exactly. The band structure is gapped, but the chiral edge states are gapless. Absolutely. It's guaranteed by topology, right? This Chern number and so on. And this was possible to measure experimentally. It was the cover of Nature Physics in 2020. Light-induced anomalous Hall effect. And you can find this and compute this plateau and so on. And here you can see this GXY that is, as Neto asked, it counts basically the number of edge states. Each edge state contributing to E squared by H, to conductivity. So 1.8 is what they find. Recall that without the light, it would be nothing like this, nothing like this. Yes, this is something that we are definitely not going to be able to address this week, but you can take this theory that I'm doing here. You can make it slightly better, including the effects of temperature and some of the leading out of equilibrium effects. And one of them would be to find an effective temperature. That you say, well, this is absorbing some heat, but you can still model as a Fermi-Dirac distribution with some effective temperature and so on. And it's possible to show that the plateau can be deformed and it can be fit to this more. It is topological in nature.
But we know that the plateaus are nowadays used as standard measure.
Not this one. Not this. Lots of fluctuation. This is true for the plateaus in topological insulators as well. I mean, this is a fragile version of the integer Hall effect plateaus that are much more robust. But yes, there are, I can send references or put references in which calculate some effects that I will not be capturing here. But these are, as long as if you assume that you have this Floquet plateau that I told you about last lecture, and you would get precisely 2.0, if there's nothing else. The problem is that nature has more to offer, let's say, than just that. Okay, so this is in a sense proof, and again, this experiment it's quite convincing about what it is doing here. And since graphene is so nice and simple, we can do more theoretically. I will just briefly tell you what else we can do. It's a great playground. It's a great playground. So what else can we do? Well, I told you that there is a gap. And you may not be completely convinced, because I showed this gap by doing one order in perturbation theory. And you can say, well, maybe if you sum the entire series, they cancel out in a very peculiar way, and this gap doesn't exist. Okay. So what I will tell you is that if you have a cone, this can be any gapless cone, actually, or any gapless system. It could be a parabolic band touching as well. It doesn't have to be this particular cone. So if you have a cone here, and you shine light, you are going to open up a gap, which is equal to, this is for circularly polarized light, 4A0 squared plus omega squared minus omega. This is exact, okay? This is the gap. You may not be convinced because you have a Bessel function there, but if you sum Bessel functions, it is possible to get this thing here. The way we do it, there is one approximation actually. We do minimal coupling of this K.P model. So we are going to neglect any curvature of this cone that would come from subleading terms. And this, by minimal coupling, becomes sigma dot K plus A of t. And then you take this A of t, we know A of t, I just wrote it down. So it's a cosine and a sine. You do the Floquet engineering of this model here. So you do the Floquet engineering here. And then you set k to 0. So this k is a deviation, so this cone is centered at k equals to 0, okay? So this k is the deviation from the position in which you have a cone. Around this, recall you had a cone k and k prime, okay? Two cones, and this is the deviation from k or k prime. And when we want some quick calculation like this, just go to momentum space and do the minimal coupling in momentum space. It's completely equivalent to what we had before. And this problem is the spin half problem that we solved yesterday. It is identically the same. If you write down the Floquet matrix of this problem when k is set to 0, first you do minimal coupling, then you set k to 0. Okay, fine. Now you have a problem that is sigma dot A of t. I think at this point you are already convinced it's the same problem as yesterday, right? This is a cosine of omega t, sine of omega t, and you find the same gap. You just have to be a bit careful, and tomorrow I can show you some other band structures to find what is this value here. I told you yesterday that we had levels like this, and they repeat. But it turns out that they can cross as well, so they can repeat and cross. So they can do this. And then you have to think carefully, what is the gap and so on. And this is the only thing you have to think carefully about. This part is the same as before. And it turns out that this is the gap. We can discuss why this is the gap. It turns out that if you don't choose this minus omega, everything else is greater than omega. So if you set this to 0, this is greater than omega, so this is already the other Floquet zone. So in order to be putting these energy levels inside the same Floquet zone, you have to conclude that this is the gap, okay? It fluctuates very fast, that is true. Your gap goes to 0. I would like to start by pointing out that this is completely consistent with this omega going to 0 here. But yes, it is a question, if you think physically what's going on. If the frequency goes to infinity, the field is oscillating so fast that the electrons don't have time to react. When the electrons start to react, it's already rotating again and so on. So it doesn't work very well for some particular effects, yes. True. True. Yeah. It does. Yes, that's true. It depends on how it was before. Like if you had a metal before, it just doesn't react to the light, but it still remains the same way as before, okay? Even if you set omega to be just from this point, if you set omega to be very, 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 very large, this is still order 0, okay? This is still to order 0. All right. So now I'm talking about tricks, because these are cute examples that you can include in your toolbox if you're ever going to solve a Floquet problem in real life, so we need as many tools as possible. Another way of opening up this gap, and it's not completely useful for this particular problem. It's actually harder for this problem. But keep this in mind, because if you need time evolution, it's going to be easier, what I'm going to say next. So now it's just playing with graphene. So this is trick number 1, to see how you open up a gap non-perturbatively. Trick number 2 is let's simplify the time evolution. So that if you think the time evolution is too complicated, okay, so if you think the time evolution is too complicated, there is a way to make your life simpler. Tomorrow I'll be talking about our famous U of t, the time evolution. What is the time evolution between two different times in this Floquet engineering? Can you just take the Floquet Hamiltonian, exponentiate it, and take this time difference? It's not exactly like this. The Hamiltonian is time dependent, and at different times, it does not commute. The two Hamiltonians at two different times don't necessarily commute. So we have to be careful about time evolution. But this is for tomorrow. I will propose a protocol. So I'll propose a protocol that has 4 steps. This is also very common. Even in the context of some time crystals, it's possible that you have half of the period you're doing something and the other half something else, just step functions. This is not uncommon to have step functions during your evolution. So I will propose, just to, and again, this is just a trick or just for fun, okay? But it can be helpful as well. So I will propose to drive the system the following way, around this Dirac cone. Just 4 steps. 4 steps. So in this case, I will just write it as K minus X dot sigma. K minus Y dot sigma. K plus X dot sigma, and K plus Y times sigma, and this is for times between 0 and a quarter of the period. This is for a quarter to half. This is from half to 3/2. 3/4, and this is from 3/4 to T. What are you doing? You're trying to replicate a circularly polarized light by discrete steps. Instead of making the light rotate like this, you accumulate the phase here for some time, the phase here for some time, the phase here for... So it's a discrete, clearly a discrete version. It still rotates. This thing is rotating. But you just accumulate 4 step functions. So your drive is going to be 4 step functions pointing along 4 different directions. In principle, you may be worried that this can lead to kinks that are not completely, you're putting it by hand, because at T/4, this is not continuous. And you could be right. But the great advantage is that this Hamiltonian commutes with itself for this entire time. So for 1/4 of the period, you have commuting Hamiltonians, and then they don't anymore. If you recall from your quantum mechanics course, how to write down the time evolution operator, it involves time ordering. It involves time ordering because the Hamiltonian at different times may not commute. And this one helps. It's helpful to have something like this. And since we can solve the problem so many different ways, this has a gap, so you can compute this gap perturbatively. I only found this article, this paper that computes it perturbatively. I'm not completely convinced that this cannot be done analytically or in all orders, okay? 1 by omega, 4 omega, A0 squared. A0 squared, okay? Okay. This is the gap that is going to open up. And you can, as an exercise for home, see if all these things that I'm writing down, if they agree or not. I already wrote 3 possible values for the gap, and you can see if they agree or not. In the cases that they don't, why wouldn't they agree, okay? I will leave you this as an exercise as well. Very good. Very good. I will finally present another thing that we can do with graphene, because why not? Another trick. And this is, I consider this to be an important evolution in terms of Floquet engineering over the last 6 or 7 years. That is to go beyond monochromatic light. So now, so far, we only had 1 frequency. We had 1 frequency, and we were very happy with our 1 frequency. It's producing great results. But sometimes it's not sufficient. Sometimes what you want, you don't find. And what can you do in those cases? You can combine two frequencies. If these two frequencies have a ratio that is an integer, so let me explicitly tell you what I mean by that. So now we have light, periodic, of course, but now this light has two frequencies. This is called bicircular light. Bicircular light, okay? This is an advanced, this is a profile polarization. Again, this is another knob. The knob, we so far talked about monochromatic light. I'm proposing this thing as a novel just because this is the first time we are seeing it this week, okay? This was studied for graphene, of course, first. One of the first cases is for graphene. And I will write down the reference here, but I will also put them, I will make all this available online. So if you go to the website that I told you yesterday about, or on Monday, there is a list of references. And you can find all these references are listed, okay? So this is from 2019. And also to advertise to another work that is not in graphene, it's in cadmium arsenide to our colleague Thais in São Carlos. She also has been doing Floquet engineering, and she considered this for cadmium arsenide. So that's PRL 128 066 602 2022. Okay. So these are examples, and this was done recently, much more recently, in strongly correlated systems as well. Okay, I will bring some references for bicircular light in strongly correlated systems starting probably tomorrow. Tomorrow we are going to finally start talking about strong correlations in Floquet. It's a thin film. Thin film. And you can find interesting things. So the bicircular light, I will not, again, give a full course on bicircular light. It's electrodynamics, end of the day, of course. So you can choose A of t that you can write down as AX plus I AY. And this is AL e to the I omega t plus AR e to the minus 2I omega t plus theta. Okay, so you have two frequencies. Here you have frequency omega and 2 omega. So in this paper, you consider not omega and 2 omega, but omega and let's say p omega, where p is an integer. And if you draw this profile, it looks, you can choose these phases properly to look at like this. Okay, I'll just cheat and draw it like. Okay. You may be able to break fewer symmetries by choosing this, as compared to linearly polarized light. So in a sense, this bicircular light has a flavor of circular light in the sense that it clearly rotates. You can see this. If you do this first and then this and this, it goes like, you put arrows like this. You have a sense of chirality. But at the same time, it has a flavor of linear polarization because you have very specific directions. That's why it's potentially interesting. It could be the best of both or the worst of both, but it typically works. It's very nice, okay? This was done for graphene first, but then you have to really explore a bit more Bessel functions because the Hamiltonian becomes more complicated. The hoppings are now, I'm not writing them down, but they become something like this. Sum over m, Jm plus 2n AL times Jn of minus AR, and AL times phases here. I will not do this. This is too much for this week, but this are going to be the effective hoppings, okay? You can solve this problem, you go to IFSC or any other book with many identities on Bessel functions, and you can decompose the integrals like this, the product of Bessel functions. And again, if you're very enthusiastic about Bessel functions, you can choose these parameters, one of them to be 0, and resum the series, or sum the series to produce one Bessel function only. You have to recover the limit of one circularly polarized light. If you set, for example, AR to 0, then you recover this. There are several limits that you can recover, okay? But this is a bit much. I will not do this algebra, but just to advertise this frontier of using other types of polarization. This is novel and quite interesting, even experimentally. The main motivation comes, you can do this experimentally, okay? You solve problems that, for graphene, and for the cadmium arsenide. The cadmium I'm more familiar with. You can find this, it's topological phases that are beyond what I just told you now, in particular these axion insulators. These are topological phases of matter, or there are many topological phases of matter. First, it would be an entire mini course about this, but I would say some of them break time reversal, some of them don't. And some of them you can combine symmetries in a very specific way, like all of them, to find very interesting topological states. And the axion insulators are candidates for topological phases as well. So the question is how to realize this topological insulators, this class of topological phases. A possibility would be to be using this type of light. So it's a big family of topological materials that we would like to understand better. Okay, there are the crystalline topological insulators. There are many types of topological phases that can be described by some band structure, and this protocol allows you to play with that band structure and compute the topological invariants. Again, this would be an entire different mini course, but the point is, given a band structure and given the eigenstates, you can compute topological invariants, and they may be different according to the choices of polarization profiles. That's the main message. And some of them are only accessible if you have profiles like this. Imagine if you have a lattice that has bonds along these directions. So, for example, you can already see that this has a flavor of circularly polarized and a flavor of linearly polarized, and so on. Okay? Questions so far? Okay, so I think I ran out of tricks for graphene. Okay. Uh-huh. Yeah, no, this is... No, absolutely. Right, this is not, I would say, off topic. It's completely a very relevant question, because if you do all of this and then you go to a lab and people tell you, oh, this is impossible to make, so what is the point? And I would tell you that the frequency of light is not the hardest part. Sometimes you have to be a bit careful to avoid what we are going to study more tomorrow. These are resonances. So if you have a system with many bands, as any material has many bands. But if you have bands like this, and it turns out that you choose a frequency that is a high frequency, but then it connects exactly these two bands. It's a problem, because you start pumping electrons from here to here. I would say this is the major point of concern, because you can produce lights with high frequency, that's completely fine. But if you want to measure a plateau or that number, G, X, Y, you need to have the laser on, but you also have to measure that at the same time. So these two things have to be done together. But you want to avoid all these effects here. So this is a topic I will not be covering this week. We don't have time, but it will be a natural extension of this mini course to start thinking, well, if this is almost resonant, so the first thing to do would be Fermi's golden rule to see what is the matrix element for this transition and so on. Because if they resonate, but the matrix element is 0 for some symmetry reason, let's say, then it's not a reason for concern. But I would say the main concern is resonating that would destroy the plateau. Remember, we had this plateau schematically. Things that would destroy the plateau are the main reason for concern. Okay. This goes beyond what I'm doing here. Here, even if you find a light that is completely in resonance, nothing here would collapse at this point. Because, I mean, I'm considering graphene with just these bands and nothing else. More questions? Okay, let me briefly introduce you to another non-interacting model so that tomorrow we can have the entire lecture about interactions, okay? About strongly correlated phases. So the next one is in principle simpler than graphene, but I think graphene is simpler actually. Okay, so all right. So what is the next model? Next model, and the challenge for this next model is actually to find the bands, because it becomes a slightly complicated model in real space. So in a sense, what I'm going to describe now is a very nice exercise of solid state physics. You're going to see why. So let's start with a chain. So if we start with a chain, and then we want to see, so again, I would just give the title to this of a simple 1D model, and for the lack of a better word, call it effective dimensions, okay? Effective dimensions. It's still going to be the problem of finding the band structure of a simple system. So consider the following Hamiltonian as a function of time. Minus sum over J plus delta 1 cosine of omega t. I will need more space here. Okay. Minus 1 to the power j, Cj plus 1 dagger Cj plus Hermitian conjugate, plus delta 2, sine of omega t, sum over j, minus 1 to the power j, Cj dagger Cj. Okay, this is the Hamiltonian for the following chain, so, or for the following one-dimensional system. Okay, so I don't think anybody wants to leave now with this rain, right? So we can go until, I don't know, 8 p.m. with this lecture, no? Because I mean, it's impossible to leave now. Even better. I mean, I have enough material prepared so we can keep talking, so I can keep talking until tomorrow. All right, so this one is going to be delta 1 minus delta 1 cosine of omega t. And this is going to be delta 1 cosine of omega t. These are hopping terms. So the only thing that matters is if j is even or odd. Okay, so it's like this. All right, and this is delta 2 sine of omega t. And this is minus delta 2 sine of omega t. So these are, you can think of this as an oscillating chemical potential of some sort, but it also changes sign. So according to the value of J, so for this one, I would expect the J to be odd. So, well, let me put it here. There is 50% chance that this is plus and or minus. I don't know. You can check. But this is the setup, okay? So far it looks artificial and so on, but we can do the same technology as we usually do. We can find the components HM. So this one is, again, simpler because it doesn't require Bessel functions. So if you consider, the Bessel functions are, it's only calculation actually, but if you consider simpler to just Fourier transform the cosine and the sine here, fine, you can just, this problem is slightly simpler that way. So it's minus sum over J, Cj plus 1 dagger, Cj plus Hermitian conjugate, delta M0. So this, it's just this term here. Okay, but I forgot to put the coupling J here. Okay. Plus delta of M1. And again, this delta has nothing to do with delta 1 and delta 2, okay? These are the Kronecker deltas. Sum over J minus half Cj plus 1 dagger Cj plus Hermitian conjugate delta 1 times minus 1 to the power j. It's a bit lengthy. That's why I think like graphene is simpler. Delta 2 by 2i, sum over j, minus 1 by j, Cj dagger Cj, plus delta of m minus 1, Hermitian conjugate of delta m1. Okay? Recall that the m and minus m are related by Hermitian conjugation. You can recall that in order for the entire Hamiltonian to be Hermitian, this is always the case. All right, so we had the one-dimensional chain, and now we have. It's coming, it's coming. Not proposal, but this is going to be, and again, I just want to engineer models. This is going to be, to realize, this is more theoretical, but it's going to be Thoules's original proposal of charge pumping. So this was a proposal, I think, from the 60s or 70s of this 2D model, which presents this charge pumping. And what I'm going to show you, and this comes from questions that I got yesterday. So yesterday, many people came to me when I wrote down this replica, or the day before yesterday, this replica scenario in which I would put this and write schematically like this. And some people told me, well, this reminds me of a chain along this direction. Or this, in each block here, I have a model, but then it's a chain in which I'm connecting all of this. And then I realized, well, this example is precisely that. Okay? What is going on here? You have now hoppings along the one-dimensional chain, but now we have hoppings with this M term, okay? And you can write down the Floquet engineering, the Floquet Hamiltonian. You can write the Floquet Hamiltonian, and I will do it briefly here, again, because this is, the question that I got the most was the confusion about how to take this and write as a matrix. So let me do this very briefly here. Again, using the correct signs here. Until yesterday, we had the wrong signs, but now this has been fixed. H minus 1, H minus 2, H minus 1, H1, and H1, and so on. So let me emphasize this once again. Even if I have only cosine and sine here, which means that I only have m equals to 1 or minus 1, this matrix is completely populated. Okay? You put the h minus 1 all the way along this diagonal and all the way along this diagonal. So these h1s and h minus 1, not to be confused, and this was the source of confusion, with the label of the states. So this state here is 0, this state here is 1, this state here is -1, and so on. And then I got this question many times. So if this is 1 and this minus, so the only finite block is here and here. No, this is not true. We call these states with a definite number of photons. So this is just the jargon. So -1, so emission of a photon, 0 and 1. And what the Floquet terms do, they move you around different sectors. So H-1, you should think of H-1 as a term that is going to emit 1 photon. So you start from 0, you end up in -1, so emitting 1 photon. So, but you can also start from 1, emit 1 photon, and go to 0. So don't confuse having only m equals to 1 and -1 here with not having this matrix with many, many non-zero components, okay? This was a question that I got a lot during the exercise session yesterday. Okay, just to finish the lecture, or not to finish the lecture, to continue the lecture with this example and finish this example. I will take this analogy, not this analogy, but this scenario very seriously now. So each replica here, if you will, each sector will have a 1D chain. So I can draw it here like this. These are the sites, and I will literally replicate the sites, okay? And now you can think of this HM and the Cs as a two-dimensional model. And that's why I told you that it's a solid state problem. It's not the simplest, because the first thing that you're going to notice is that you have 2 sites per unit cell. This is not very hard. The graphene was also like this. But you have to write down all these terms here in real space. I'll just do this schematically. And if you have time to diagonalize this in momentum space, then you can show to me and we can compare our band structures, okay? But it looks like this. This hopping is -I delta 2 by 2, while this one is I delta 2 by 2, and this one is -I delta 2 by 2. So these are terms, if you look here, that are not going to change the J value. So this is M, and this is J. So they do not change J, but they do change M by 1 unit. So it's really a hopping structure, really a hopping structure. Okay, and then, this is already interesting, but we have more. We have this connected along the diagonal with delta 1 by 2, and then this is going to be minus delta 1 by 2, delta 1 by 2 like this, delta 1 by 2. You can see delta 1 is here, so it's changing both M by 1 unit and changing the C, J plus 1 to C. And you can continue putting all the terms here that are, you have just one that is significantly simpler. You have a J term here. This is the J term. This is definitely a 2 by 2 or a 2-dimensional lattice. You can diagonalize it. You can just go to momentum space. The way you do it, the way I would do it is by choosing these 2 sites here. These 2 sites, for example, as the unit cell. And you write down everything. There are terms that are within the unit cell. There are terms connecting the unit cells. You diagonalize it. And what I didn't write, but it's important to realize Pauli's original proposal, is that if you notice here, from our diagonal, for each M, so this is, let's say, this is M equal to 0, this is M equals 1, M equals -1, and so on. And the J is just a regular label. You can also label them as 1, 2, 3, and so on. Okay? This is the 1D problem, and this is the problem in Floquet space. There is this term along the diagonal. So the -1 sector that is here, all the sites along this chain here, let's say that this is the -1 chain, will have a chemical potential term that will be, or intrasite term, omega. Omega, omega, omega. Here, 0 omega, 0 omega, 0 omega. Here, -1 omega, -1 omega, -1 omega. And so on. So we have a hopping problem, great, but we also have something that changes from 1, 0, -1, and so on, -2, -3, -4. And this mimics a static field. So if you apply a static electric field, an electric field that is time independent, and it has some strength omega. Recall that if you have an electric field, what you need in terms of the energy, you need the line integral of the electric field. That is the potential that you get, okay? So the potential is going to keep increasing and increasing and increasing, or decreasing. I will not comment much about the 1 or -1. You can do it properly such that the field is along this direction. So it's a time-independent field along this, let's say, synthetic or effective direction. So you have the field here. For the different Floquet sectors, you have hoppings and all of that. You can diagonalize this problem at this point, okay? You just find the band structure and so on. You can first and more easily solve this problem if you set this, if you neglect this term that is going to keep increasing this, because this is not identical to this as the frequencies are not the same. So by setting this to 0, which is very artificial, you can solve it in momentum space. If you put it here, then you don't have translation symmetry anymore because you have this potential, electric potential, giving you finite different energies along different lines, okay? And this was the model. This realizes, and again, it's not the point here to solve the problems that we are proposing, but this is the Floquet version of this is called, this model in which you have a 2D lattice and you put a static field along one direction. This is the original proposal of what is called Thouless pumping. Thouless pumping, okay? And the idea is you put a static field like this, and then you're going to produce a current along this direction, and this current is perpendicular to this, so it's going to be some J that is a current, J current. It's going to be some sigma that is perpendicular times this omega. So the sigma is some conductivity, okay? So again, forgetting for a minute the Thouless pumping, if you have never heard of this, I will also put the reference. But the point is that this model realizes what many of you were asking me yesterday about how this replica structure looks very similar to an effective dimension or tight binding along this dimension. So this model, this 1D chain realizes that you have a new label M, and then you have dynamics or interesting features along this direction M. One may even wonder, can you localize, can you do localization along this, or any interesting phenomena along this direction? This is a possible question, for example. Like, what can happen? What is the most interesting thing that can happen along this direction, okay? So far, this direction gave this effective time-independent electric field with amplitude omega, okay? Do you have questions so far? Okay. Uh-huh. Yeah, yeah. This, you can do a lot of things. To eliminate this term omega completely is tricky because the first thing, if you write this down, no matter what are these H zeros and so on, it's this omega 0, omega minus 1, omega, and so on. It will naturally appear. So you have to cook up something that eventually cancels all them out. This is not simple to do. This is not simple to do. So, there are ways. If you, again, in the case of graphene, if this omega, it depends. This omega is a parameter in your problem. If you consider omega to be very, very, very large, then you can do expansions in powers of 1 by omega, and then this naturally will go away. But then you're losing this extra dimension, right? Because it's a 1D problem with new hoppings. Here we are actually trying to solve the entire 2D problem, but I'm not aware of any simple idea that would completely eliminate this, but given that I know that there are many different proposals of how to play with this extra dimension, and I will put 2 or 3 references there so you can have a bit of fun with the extra, or sometimes called effective or synthetic dimension, okay? All right. Yeah. That's right. It is similar. The first thing that I would like to tell you is that there is a way to classify all the topological phases coming from this type of Floquet systems. It's subtle, and it's not identical to the case in equilibrium. Here, this has been done in these classes. I don't know, for dependent problem, I don't know, there are 10 classes, something like this, right? So you can go one by one, this A1, A2, all of these classes, and see what would be the analog here. And at some point, there are subtleties, because we also need, I mean, here I'm talking about quasi-energies and so on, but this is, to classify, you actually have to look carefully to the states, to the eigenstates. It is more subtle. It's an important question that has been answered over the past 5 or 10 years, but it's beyond what I'm telling you here, and there are subtleties. At some point, you are going to notice that this is not a dimension like any other spatial dimension. Mm. Yeah. Yeah, as Neto was pointing out, asking if you can get rid of this, you can try. And all of these questions are actually interesting and important questions, and you have this is a huge field, and you have groups trying to do exactly what you are describing as well. I am not aware of any successful case of doing this. Let's say if you have a problem that has a very nice solution because it's 1D, but then you do this and somehow you solve the 2D problem because you're doing this trick. I'm unaware of any possibility, partially because several ingredients will appear naturally and they are hard to avoid. So it has to be a structure like this. It's not. If you start with a one-dimensional problem like I did here, I was carefully choosing this to produce what I wanted. And this is what I wanted. But if you have an integral model or a model that you can solve, you have, and again, it's just a matter of thinking of a very clever protocol. You can take your favorite model and see if by putting a very nice protocol here or a very smart protocol, you can solve an effective model or an effective 2D model that is new. All of these are possible scenarios. Okay, more questions? All right, so at this point we are done with the non-interacting part of this course. So starting tomorrow, we are going to take a different route, but it's not really different because our starting point is always going to be the same, but I would like to ask questions about systems that are strongly correlated. So here, end of the day, I started with electrons hopping around and I ended with electrons hopping around. Is it possible to take systems in which we have strong Coulomb repulsion, for example, and do the same protocol that I did here. Is this possible or not? So the answer is, it is possible, and we're going to start doing that tomorrow. So tomorrow and Friday, we are going to be talking basically about strong correlations and Floquet systems, and I'll be doing a little bit extra regarding the theory of Floquet systems, in particular addressing the basics of the time evolution, okay? So that's for tomorrow. We start tomorrow. The first lecture will be continuing from this particular point, and then bringing the correlations, okay? More questions? All right, if not, we continue tomorrow morning.